write the local U1J. Okay, so let's consider it for the complex scalar field and see what is happening there. So let's go to the complex scalar field again. So we are having this partial mu phi star minus n square phi star phi. Okay, where this phi is equal to phi 1 plus I phi 2 by rho 2, and this phi star is equal to phi 1 minus I phi 2. Right? Clear? Okay. So if I calculate now, you can calculate the Klein Gordon equation. So you are having these equations are satisfied for both the fields. Phi is equal to 0. So this we have already done in the last lecture. Okay. So now if I consider, so let's rewrite it. Let's rewrite this Lagrangian. Okay, since if you use phi and phi star in this very Lagrangian, in this way, you can put this Lagrangian in this form. Okay, sum of two Lagrangians. Clear? Okay, so what I will do, okay, so it will correspond to simply the sum of a Lagrangian corresponding field phi 1 and a field phi 2. Clear? Okay, so let me write this phi as in a vector notation. Let's write in terms of the vectors, two fields. So you are having I, where I is the one direction, phi 1 plus j phi 2. Clear? So let's put it, since it's a two component field, I will make it as a vector. A vector having only two components. Clear? Got it? So then how I can write this Lagrangian? It will be simply partial mu this phi dot partial mu phi. Clear? So I'll put a dot now, because if I'm using the vector notation, so I'll put a dot. Clear? So minus. So this will help me. So phi dot phi. Okay. So this will be when we will do the multi-component fields. Okay, more than two components, then dot is okay. Let's say this phi can be having n components as well. Clear?
So is this phi star form?
No, I have put it in terms of now phi dot phi. So what that will give me? So it is this Lagrangian. Okay. So you are having partial mu phi 1 partial mu phi 1 plus partial mu phi 2 partial mu phi 2, okay, minus m square phi 1 square plus phi 2 square. Clear? So when you use these objects here, what you will get? Sum of two Lagrangians. Clear?
Yes, sir.
Got it? Instead of writing it in this way, I have introduced a vector phi. Clear? Having two components. It is the same thing. Rewriting the same thing in a vector notation. Clear? Got it? Okay. So it is a dot product now, like this thing. Okay. So why this kind of notation is useful when we look at the n component fields? So then it makes sense. You cannot put n component field in this very fashion. Okay. So this was just to show that you will be having, this will turn out to be the sum of two real fields. Clear? Okay. So now let's go to our problem. So if I take this global U1, okay, clear? So how the fields go? So this phi goes as e raised power minus, let me write minus lambda phi. Clear? So I last time wrote as q theta. Theta was a parameter and q we said it is the charge. Okay, but that q, okay, you will see that we have introduced by hand. Okay, so there was no reason why you have to put q. So I will use, instead of q theta, I will put simply lambda. Lambda is some number here. Okay, so if you write this as an infinitesimal one, it will be simply 1 minus I phi. Okay, so that's equal to, so in other words, your phi under infinitesimal rotation, okay, infinitesimal case, this phi goes as phi minus I lambda phi. Clear? So as an infinitesimal transformation. Okay, everybody got it? Okay, so what is therefore the change? Therefore this infinitesimal change is equal to minus I Okay, got it? Okay, now so let's look at this thing. Let's look at this derivative. So partial mu phi will go as, okay, so let's take the derivative of this object. Partial phi will go as partial mu phi minus I, since lambda is a constant quantity, so it will be what? Partial mu phi. Clear? Or in other words, the change in, so the variation in this phi, partial mu phi, so this will be simply equal to minus I variation. Clear? Can I write it? Any problem?
Yes.
Okay, so now look here. So so the transformation rule for phi and the transformation rule for this derivative of phi, they are the same. So they transform in the same way. So so look here. So you are having phi. Okay, so this is minus I lambda delta phi. Now let's look here. So you are having partial mu phi. So it is minus I lambda. Okay. So what it is
Delta
equal to?
partial mu phi.
Sorry, it is not delta, it is phi. So it is partial mu phi. Clear? So why no? So it is not delta, because you take it here, this minus this thing. Okay, so it is delta. It is like this thing. This is a prime is equal to this minus this. Clear? So that will give you a delta. So now look here. So the rule for phi and delta, this derivative of phi, they are the same. So you are having the same object here, same object here. Okay. So in other words, they transform in the same way under local u1. Sorry, not sorry. It is global u1. I have not considered it local. Okay, under this kind of phase rotation. Okay, got it? Okay, so you can calculate now. So what is the current? Okay, one more point. Okay, so you can now calculate the current. So this neither current you can calculate since you are having an invariance. So this okay. So if you put this phi in this very case, so what you will get? So Lagrangian will be invariant. Clear? So let me say. So under this thing, so this implies what? This lambda prime. Okay, so Lagrangian same, or I can say the change in Lagrangian is 0. Okay, so it is an invariant object. So it is invariant under this e raised power minus I lambda phi lambda. Clear? Got it? So if you are having an invariance, okay, so it implies there is no other current. Okay, so I am just repeating last lecture. So it is simply G mu. So what will be that? Anybody? Yes? So it is partial L by partial mu phi delta phi plus partial L by partial mu phi delta phi star. Kind of this thing. Since there is no variation x, this kind of transform, it is in the internal space of the particle, internal space of the field. We have not done. Okay, so here, so there is no variation in coordinate. Okay, clear? So this transformation purely is the transformation within the field, as we call these as the internal symmetries. Clear? So think of the spin. Okay, it is an internal variable. Okay, if you are having a transformation corresponding to the stiffener of the particle, so that will represent an internal symmetry. Clear? Okay, symmetry reflected within the, say, let's say within the spin space. You are not displacing the particle. You got me? The way you are having a coordinate transformation. I have not done any kind of coordinate transformation here. Clear? So there is no variation in coordinate. Okay? So in that sense, we call it as an internal symmetry. Okay, how much is this thing? So it will turn out to be phi partial mu phi star minus, okay, phi star partial mu phi. Okay, so this is your current. Now let's have remarks. So you can have the conserved quantities. Okay, so what is your conserved quantity? Charge. So that's equal to J0 integration over d3x. So how much is that? So it is I integral d3 of x phi star partial phi by partial t minus phi partial phi star by partial t. Clear? So this is a conserved quantity. Okay. So the first thing is, so the first remark is that from the invariance under this global U1, what we call, okay, you are having a conserved charge. You call it as a neither charge. But the point is that it does not reflect the conservation of the electric charge. So it is some charge. Okay, it does not give us any hint of the electric charge of a particle. The usual electric charge, what we know, huh? We don't have any kind. Okay, so from here it's not clear whether this charge is the electric charge of the particle or something different. Clear? Samajh hai? Is it? Is there any charge, electric charge? So you don't have any kind of electric charge here. Okay, so you will see in a moment where the electric charge comes from. Okay, and second point is that this is a purely classical quantity. It does not carry any kind of H-cross. Okay, since we have done purely classical field theory, no quantum, we have not done any kind of quantumness here. So it's a classical object. Okay, and anything more? Or you can think. Okay, so we know. Charge is quantized. Clear? It comes as the integral multiple. So this quantity does not give us any kind of information. Let's say if I quantize field phi, it does not give us information whether charge is really quantized or not. Okay? So under that means, under this global U1 symmetry, we don't have any kind of information what the charge is. Okay? What kind of charge the particle carries. Is it quantized or not? We don't have any information. Clear? Samajh hai? Okay. So how to okay, have you got the point? Okay, so now let's move ahead. Now let's look at this transformation rule again. So you are having this transformation rule, phi goes as what it is equal to, so e raised power minus I lambda phi. Clear? Clear? Okay, so let's write it. Since it's for both the components phi 1 and phi 2, so that means I can write it as phi 1 plus I phi 2 goes as e raised power minus I lambda phi 1 plus, okay, I phi 2, and phi 1 minus I phi 2 goes as e raised power I lambda, because it is the conjugate of this thing, phi 1 minus I phi 2. Clear? Okay, so what it yields me? So let's calculate phi 1. How phi 1 will go? So you just add the 2, you will get phi 1. Okay, it goes as like this thing, phi 1 cos of lambda plus phi 2 sine of lambda, and phi 2 goes as minus phi 1 sine of lambda plus phi 2 cos of lambda. Okay, in other words, you are having this quantity, this phi 1, phi 2. So let me write it as a prime. So it is like this thing. So this is the transformed one. It is cosine of lambda, sine of lambda, minus sine of lambda, cosine of lambda. Okay, so phi 1, phi 2. Clear? Okay, so you started with a, so what this represents? So you are having U1 is equal to e raised power minus I lambda, and lambda belongs to what? 0 to 2 pi. Clear? So all the elements on the circle. Okay, so now what you have got? You have got actually a two-dimensional rotation of the field. So that means this transformation represents simply a rotation in a two-dimensional plane. Clear? Okay, so what we call, so it is an orthogonal transformation, because this form is an orthogonal matrix. Clear? Okay, so what is the determinant of this matrix? that is 1. Okay, so if I call this as an orthogonal transformation in 2 dimensions, but there is a determinant equal to 1, clear? So I will write it as a special orthogonal transformation in 2 dimensions. Okay, got it? Okay, so therefore I can have this SO2 is isomorphic to this U1. They are having the same kind of a transformation. Got it? Okay, so now here is the point. Since this lambda does not depend on any kind of coordinate, clear? So when I make a transformation on a field, okay, let's say in the internal space, so this is some internal space, at a given point I make a transformation, clear? So what will happen? Since this does not depend on the coordinate, it means all the points in this very space get affected at the same time. Clear? So it is simply you are making a phase change, so everything will get affected at the same time, simultaneously. Clear? So what the principle it violates? Principle of relativity. Clear? Isn't it? So if we take this seriously, this kind of condition, I mean to say okay, so from the theory of relativity, if I make a transformation, okay, let's say if I try to have an interaction at this very point, it may propagate to the another point at certain speed, clear? At the speed of light, at maximum. Okay, so that means one point will get affected first and the other points will get affected later. You got my point? So that is the theory of relativity. But what this transformation says, it means all will get affected at the same time. Clear? So it violates the spirit of the relativity. Clear? What to do? So in that case, okay, so if so in that case what I will do, I will simply gauge this lambda. What I mean by that, I will simply say this lambda is a function of coordinate. So that means if I am making a transformation at a given point, so the other points will get affected later, because it will then depend on the coordinate, how it varies with the how this lambda varies with the coordinate at a given point. You got my point? What I mean by that, okay, instead of having this global object, so instead of having this globalness, okay, what I will do, I will make this lambda to be dependent on coordinate. So what will be our phase rotation? Okay, so now this phi will go as e raised power minus I lambda x phi. Clear? So now this will depend on coordinate, okay, every point x. Got it? So this kind of transformation we call as a local U1 gauge or gauge transformation of the second kind. Okay? Now we need to check whether our Lagrangian remains invariant or not. Okay? So since I have, we call it as I have gauged the symmetry. Okay? I have made it as a coordinate dependent. This symmetry is a coordinate dependent quantity, and under this symmetry I need to figure out the invariance of the Lagrangian we started with. Okay? Or how we can ensure the Lagrangian is invariant, or what are its consequences? We need to figure out what are its consequences. Okay? Clear? Okay, so let's move ahead. Okay. So first thing, since if we are considering the infinitesimal, so let me write for the global case. Okay, so you are having this e raised power minus lambda phi goes. So what you are having here, delta phi is equal to minus I lambda phi, and then you are having variation in this quantity. So this is minus I. So this will be correct. Okay. So let me take, since we are considering the infinitesimal transformations. Okay. So what this is, it is phi prime is equal to some e raised power minus I lambda x phi. Okay. So instead of putting these arrows on, so let's consider the infinitesimal one, because it's a continuous transformation. That's why we consider infinitesimal transformations. For the continuous group, always choose the infinitesimal. From the infinitesimal, you construct to the finite transformation. Okay. So what it will be then? phi will go as, tell me. So if I take, so it is okay, phi prime will be simply equal to 1 minus I lambda x, okay, phi, okay. So it implies therefore this delta phi, it is minus I lambda x phi. Clear? So this is how this phi transforms under an infinitesimal transformation. Clear? Okay, so now let's check the derivative. So let's take the derivative. So I am having now partial mu phi prime, that's equal to partial mu phi minus I. So now there, since this depends on x, you have to make a product rule here. So it will be partial mu lambda phi, okay, minus I lambda partial mu phi. Okay, I will not put x now. So it means it's now the local thing. So, or in other words, so this is variation in partial mu phi. So that's equal to what that is. So let me write minus I lambda partial mu phi minus I partial mu lambda phi. Clear? Now look at the two, compare the two. So there, that partial mu phi also transforms in the same way as delta phi is transforming, okay? So you are having, both the quantities are having the same transformation, clear? Now what you are having? Delta phi, this is the transformation rule, the phi transforms this way under infinitesimal transformation, but this partial mu phi does not transform. You are having an additional term which depends on the derivative of. Okay, if it would have been, let's say, if it transforms in the same way, then this is not there. You will be having, just you have to replace this phi with this object. Rest you keep same. Clear? Got it? So that means they are not transformed in the same way. What will happen now, the Lagrangian? So that will not remain invariant. Okay, so let's check that. Okay, so let's check our Lagrangian. So this is our Lagrangian. So it is partial mu phi, okay, partial mu phi dagger, okay, minus m square phi dagger phi. Okay? So if you look at this very object, okay, let's look at this very object. It's simply phi dagger will be simply phi dagger e raised for I lambda of x. So this will be e raised for minus I lambda of x and phi. Okay? Because the function is same. Huh? So they, okay, so you can put at e raised for I lambda minus e raised for I lambda. So this will make 1. So this will be simply as phi dagger phi. So this means this is an invariant quantity. Clear? So now what I will do, so let's look at the variation in this lambda. Okay, if the variation is 0, it means Lagrangian is invariant. Clear? So let's write it. So it means it is like this thing. Partial mu phi dagger minus m square variation in phi dagger phi. Clear? So the variation in this thing will be what? It will be 0. Because phi dagger phi transforms this way and it is same invariant. So this object is equal to, okay, so this object is equal to 0. There is no variation at all. So let's write it. So let's put a product rule. Partial mu phi. Okay, then you are having partial mu phi dagger plus partial mu phi variation in partial mu phi dagger. Okay. So how much is that? So what is this variation in? So you are having minus I lambda partial mu phi minus I partial mu lambda phi. Okay. Phi dagger plus then you are having partial mu phi. Okay. So you are having a dagger. Just take I to minus I. It will be plus I then. So you are having I lambda partial mu phi plus I partial mu lambda and phi. Okay. So now just okay, rearrange the terms. It will be something partial mu lambda into minus I phi partial mu like this thing phi dagger minus phi dagger partial mu phi kind of thing. Just rearrange the terms, you will get this object. Okay. So what this is, we have just calculated. It is the current, neither current corresponding to the global phase variation, J mu. So this is simply called G mu. So you are having this variation in, so that means it is not invariant under, so you don't have the Lagrangian invariant under local this U1 transformation. Clear?
Is the second term in dagger phi dagger?
No.
This.
This is phi dagger. Huh? Yes. Okay. Clear? Everybody got it? Now what I will do, I want to make this Lagrangian to be invariant, okay, under this local U1. What I need to do? I need to introduce a term that will actually cancel this very term. Samashaman? You got my point? So what I am trying to do, okay, my aim is to make this Lagrangian an invariant quantity under this local U1 gauge transformation. Clear? Okay, for that matter, I will introduce a kind of term that will, okay, so I need to introduce a term that will actually cancel this very term. Okay? And then I have to understand the meaning of the term which I am introducing. Clear? Got it? Because Lagrangian is an additive object. Yeah? Okay, so you can add and subtract it from the Lagrangian. Clear? Okay, it's an energy function. Okay. What I will do? Okay, so I will consider a 4 vector. Okay, so let's assume some 4. There exists a 4 vector. Okay. Let's assume a 4 vector. Okay, why? Because you are, okay, so why I am assuming a 4 vector here? Forget about this very object, it is partial mu lambda, okay? So what is multiplying here?
J mu.
It is J mu, it is a 4 vector. If it would have been, let's say, a rank 2 tensor, then I will introduce a rank 2 tensor field. Clear? So, got it? So that I will show you later on. Okay, when we will take Yang-Mills field here. Okay, so I will introduce a 4 vector. Let's call that as 4 vector A mu. And for the typing, I don't know what this A mu is. Okay, so we don't have information what A mu is. It is some kind of 4 vector. It comes from certain kind of field. Okay, or you are having a field which is represented by this A mu. Okay, and you are having a vector field which is represented by this A mu. And later on we will interpret exactly what this A mu is. Okay, so let's add an additional term. Okay, now what I need to do, I need to cancel this very term. Clear? So what I need to do, so I need to have okay, so you are having this additional term, this partial mu lambda. Clear? And there is J mu. So there is a coupling between this very term and this term. I introduce A mu field in such a way that there is actually a coupling between the, so like this thing, minus E, okay, J mu and A mu. So this A mu couples with the current. Clear? In this way. Because I have considered a transformation rule. Clear? I have considered a local transformation rule which creates all these kind of problems. When I am doing a transformation, so it should also affect this A mu, is it? Got it? So if I am making a U1 transformation, so this A mu should get affected. So let's assume it is having, so under this gauge transformation of second kind. So let me use second kind to, okay, this A mu transforms this way. A mu goes as A mu plus 1 by E partial mu lambda. Okay, so let me assume this is the transformation rule. Okay, so what that means, so okay, can you tell me? So which implies therefore this variation in A mu, that is simply equal to 1 by E partial mu lambda. Okay, because when I take the variation of this thing, I will get A mu, what you get? Partial mu lambda. So that will cancel with this object. Okay, so now let's add this lambda 1. Okay, so let's take now the variation in this lambda 1. I know the variation of lambda is, variation of L is this one. Now I will take the variation of this L1. Clear? So now therefore, So this is all the assumption what I have done. Okay, so let me write this variation of L1 under this rule. So it will be simply minus E. Okay, so we need to interpret this E here. We need to interpret both E as well as A. Clear? So just be careful. Huh? Okay, so it will be this variation in J mu, A mu minus E, then J mu variation in A mu. Clear? So what is that equal to? Minus E, like this, A mu minus E, J mu. What is this variation? It is 1 by E partial mu lambda. So now you look here. So this very term. So if I write therefore, so therefore this delta lambda plus delta lambda 1. So what you get? So now add the two. That term will cancel with this very term. Clear? So what remains there? So you are having minus E delta J mu and A. Okay? Got it? So we have one more term. We need to cancel it. Huh? You got my point? So okay. So I have introduced this A in such a way so that it will cancel that very term. But what it yielded be? Another term. Clear? So we need to introduce one more term so that this is cancelled. Clear? Okay? So we have to go it in this way till we will cancel all these kind of terms. Huh? It's a trick. Huh? So now let's look what this delta J mu is. So let's look at from there what this delta J mu is. So what is your J mu? Okay, so let me write it. So you are having this J mu, it's equal to minus I phi partial mu phi dagger minus phi dagger partial mu phi. Clear? So let's calculate this delta J mu. So how much is that? Minus I. So it is delta phi partial mu phi dagger. Then okay, plus phi variation in partial mu phi dagger minus delta phi dagger partial mu phi minus okay phi dagger delta partial mu phi. You know the values of all these things. Delta phi, delta d mu, is it? So you know everything. Those quantities here they were here. Okay. So just use. So what you will get? So you will get like this twice phi dagger partial mu lambda. Okay. So therefore, what is our therefore this delta L plus delta L1. This is called just substitute the values. So you keep this here. What is delta phi? It is minus I lambda phi. Clear? And then what is delta d mu phi? It contains two terms. So you just substitute, you will get ultimately this thing. So what you are having minus, and so it is minus twice E. So delta J mu, it is this phi. Okay, let me write phi dagger phi. Then you are having this partial mu lambda, and you are having what? A mu. Okay, now you are having, if you see, you are having this field is coupled with this field. Phi is a scalar field and A is a scalar field. So I need to choose a term in such a way that will cancel this very term. Clear? Okay, so let's choose that very term. Can anybody guess the term? What should be the form? Anybody? Okay, now look here. So what you are having? So when I make a, okay, so what you are having? This phi dagger phi. Clear? So you are having this very object and you are having 1A here. So since this 1A comes, so if I am making a variation, you are having 1A. So that means the term which I must add, that should be quadratic in A. Clear? That should be A mu, so that when I make a differentiation, you will get what? A mu. Clear? So that means I need to introduce the term of the same form. Got it? Okay, so let me write it. So therefore I need to introduce this kind of field. I mean this term, sorry, not field, this term I will introduce. And this delta mu comes from where? Okay. So this partial mu lambda comes from the transformation rule. Okay. So that means my term should be proportional to this phi dagger phi and A. Clear? Like this thing. So let me introduce a term L3. So that's equal to, you are having E. So I'll write this phi dagger phi like this thing. A mu and E. Clear? You got it? Now why? Look here. Phi dagger phi is a scalar quantity. So if I make a transformation, phi dagger phi is what? Invariant quantity. Huh? Okay. Now what is A mu A mu? No, it's not. Although this is scalar, but it's not an invariant quantity. Okay. Now let's look. Okay. So let's take the variation delta 3. So it's equal to E delta up. So let me take phi dagger phi A mu, okay, plus E phi dagger phi delta A mu, okay, A mu. Clear? Okay, now what this object is? So this is, okay, so it goes as E raised phi dagger E raised for I lambda. It is E raised for minus I lambda phi. So this is same as phi dagger phi is same as this phi, it remains same. So this is equal to 0. So therefore, this delta lambda 3, it is equal to E phi dagger phi. Clear? So since this is a quadratic term, you make a differentiation. So it will be twice, okay, A mu delta A mu. Clear? Okay, so it is all the guesswork you have to create. So to adjust the terms correctly. Okay, so it is simply twice E phi dagger phi A mu. What is this delta A mu? So it is 1 by E. 1 by E. Okay. Then partial mu lambda, but I need to. So it should be E square then. Huh? Yes, I need E square here now. So I need an E square here so that 1 E cancels. Okay. So what you have? Twice E phi dagger phi A mu partial mu. Sorry. Partial mu. Now look here. What you are having? So where is that? Okay. Partial. Sorry, it's not E. It's lambda. Okay. Partial mu lambda A mu. Okay. Do you have the same and opposite terms there? So are these two terms opposite? Okay. So therefore, I have made invariant element. Delta lambda 1, delta lambda 2, delta lambda 3, it's equal to 0. Okay, so it's an invariant quantity. Clear? So now let's take a look what we have done. Okay. So you are having your parental element. L is equal to partial mu phi dagger minus m square phi dagger phi. Clear? So this was your original Lagrangian. Then what you have put? You have added that L1. What was that L1 equal to? Anybody?
Minus E.
Huh?
Minus E.
Huh?
Minus E. Minus E. J mu.
Minus E A mu J mu. Clear? So coupling with the current. Then what we have added? That plus E square A mu phi dagger phi. Clear? So these are the terms what we have. So these two terms we have added to make this Lagrangian invariant. Clear? Got it? So do you think it is a weird objective? It seems weird, but you will see it is a simple Lagrangian. Clear? Now what we have introduced? We have introduced actually a field A. Clear? Okay, so look here. So if I assume a field phi, clear? Let's consider some field phi. So this term is actually the field Lagrangian of that field phi. Clear? Got it? And if you see, these two terms represent actually the coupling. So this is the coupling between A field and the phi field, because J is the current corresponding to the phi field. So this represents the coupling between the field. Okay, I have introduced A field. So these two terms are the coupling terms, you can say. This is the free Lagrangian of the phi field. This is the coupling between A field and phi field. So that means I need actually one more term that will represent the free field of the A field. Okay, a Lagrangian, free Lagrangian for the A field. Clear? Got it? So that means I am having two fields. Let's say phi field, A field, and then there is a coupling between the two. Clear? Got it? Okay, so how to do that? I have to ensure that field must be invariant under gauge transformation. Clear? Okay, so for that matter, okay, so since the gauge transform what I have introduced for A field, okay, so A field has this kind of gauge transformation like this. Okay, so if I choose, okay, so the Lagrangian, that will, okay, so I need to choose okay, a field term, a kind of term that will represent this A. So it turns out to be this Lagrangian is invariant. So let me write, so we are L3, so L4 I will write, so this turns out to be this very object, while F mu nu is the 4-dimensional curve of A field. Okay, so if you take A in this way, okay, so you will see this is an invariant quantity. We call this, okay, so the name is there. Okay, so this we have already done. So, okay, if I am introducing a curve, a 4-dimensional, this is a 4-dimensional curve. So it is having only 6 components because it has antisymmetric rank 2 tensor. Okay, so this is a Lagrangian curve. You can see this very object is invariant under this very transformation. Clear? So therefore I will add this term here, minus 1 by 4 F mu nu and F mu. Clear? So now let's rewrite this Lagrangian in a beautiful form. Okay, so what is the field I have introduced? So this is a gauge field. Okay, so I call this A as a gauge field because it arises due to what? Invariance under local gauge transformation. Clear? To ensure the local gauge transformation of a given field, let's say here scalar field, I have to introduce this field, this A field. That's why we call it as a gauge field. Okay, got it? Okay, so and you see it, okay, in a moment we will see it's a massless field. Okay, so let's rewrite it. So I'll write this Lagrangian to be this way, partial mu plus I E A mu acting on phi. Then I am having this partial mu minus I, okay, so let me check. Okay, minus I E okay, this way, phi dagger. Clear? Then, okay, you are having minus E A mu J mu, okay, then you are having minus 1 by 4 F mu F mu. Okay, so I have introduced, these are the terms. Now you multiply, you will get exactly the same thing, and there is actually a term which represents the mass, minus m square phi dagger phi. Clear? So let me define this very object as d mu phi. It is defined as, it is known as gauge covariant derivative. This very object. It's actually, it has a geometrical interpretation. We call it as a gauge covariant derivative. Clear? So therefore I'll tell you in a moment what that means. So you are having like this thing, d mu phi dagger, okay, clear, minus m square phi dagger phi, okay, then you are having minus E mu G mu minus 1 by 4 F mu. Clear? So let's first try to understand the meaning. So we call it as a gauge covariant derivative, or simply covariant derivative. What does that mean? So it means it will transform in the same way as phi is transforming. What is the transformation rule for phi? Now tell me. let's write the transformation rule for this d mu phi. So that's simply delta partial mu phi minus plus I e, okay, variation of e mu phi. Clear? Or Isha? So let's try. Let's take the variation. So what this subject is? So you are having two terms here. What is that? Minus I lambda partial mu phi minus I partial mu lambda and phi. Clear? So plus I e. So you are having delta a mu, okay, multiplied by phi plus I e mu delta phi. Okay? So now you check it. So you are having delta phi. So this is equal to 1 by e. Okay? Tell me, partial mu lambda. What this is equal to? Minus I lambda phi. Clear? Got it? So समझ आओ? So now you adjust the terms. So once you adjust the terms, what you will get? You will get simply minus I lambda d mu phi. Kind of thing, huh? So what was this thing? Delta phi. That is minus I lambda phi. Clear? So the way phi transforms, you are having d mu phi transforms in the same way. This partial mu phi was not transforming in the same way as phi is transformed. Clear? So that is why we call this as a gauge covariant. There is a more to why we call it as a gauge covariant. So it has a more interpretation, but we'll simply call it as a covariant derivative. In a sense, it transforms in the same way as the phi is transformed under local U1 gauge. Clear? Got it? It has a more interpretation than that. Okay. So now what we have done. Now let's summarize what we have done. Okay. Okay. So let's try to interpret what is the meaning of this E. Then we will look what this A is. Okay. So in other words, we will look the meaning of A. Okay. If you see this kind of Lagrangian, okay, represents the electromagnetic field. Clear? Is that true? Got it? Okay, so you could have asked me one more point this way. Can we add this term to the Lagrangian? Okay, so let me write some L5. Can we add this very term? Let me introduce this kind of term, A mu, simply. The way you are having here m square phi dagger phi, can we add this very term, which will be simply addition to this pre-Lagrangian? Clear? So it does not contain phi field. Okay, there is no coupling between the phi field. So it will simply reflect the mass of that A field. Clear? So the way, if I interpret this m square to be the mass of the phi field, then in an analogous way, I can introduce a mass to this field. Clear? So this way. Yeah? Got it? But if you see, this object is not a gauge invariant. Now let's look delta L5. So that's equal to m square. So it is twice A mu delta A mu. So what this delta A mu is? So that's simply 1 by E partial mu lambda. Clear? So that's not equal to 0. So that means this term is not gauge invariant. Okay? So you cannot introduce a coupling with another field. So you have already introduced two fields here, phi and A field. Clear? So this is not a gauge invariant. Clear? So that means the gauge field of what you have here, so it has to be a massless. So in other words, the gauge transformation makes this gauge field, the A field, to be massless. To have an invariance under local U1 gauge, so this field must be massless. In other words, the particles which are represented by this A field have to be massless. Okay? So you have so when we are doing the electrodynamics, it is actually the special theory of relativity which required the photon to be massless. Okay? But we have introduced actually the concept of the gauge that requires this field to be massless. Got it? So therefore, an invariance under local gauge transformation reflects the emergence of massless gauge field. Clear? And we identify this with the photon field. Okay, so now let's calculate. So if I calculate the equation of motion corresponding to this A field, okay? Or let's calculate the Lagrangian or this thing Hamiltonian corresponding. This we have done already. So if I have to calculate the Hamiltonian of this field, Okay, so what I will do? So let's say your Lagrangian is what? Minus 1 by 4 f mu nu f mu nu. Okay, and there is that very coupling. Okay, so let me write this E A mu J mu. Clear? So what you will see, so this momentum, the canonical conjugate momentum, you will see equal to P minus E. Okay, since C is 1, it will be simply minus E A kind of thing. The canonical conjugate momentum, the special part. Clear? So and if, okay, so then you can see this E represents actually, okay, so you need to figure out this way. Okay, so let's write the Lagrangian corresponding to a charged particle. If I consider a charged particle for the Lagrangian, what will be the Lagrangian? What is the Lagrangian? So that's how you do it. Yeah? So, sorry, it is E like this, okay? Plus, so what is that equal to? So if you are having a charged particle, it's like this, plus E. Okay, the special components. So this will be the canonical conjugate momentum corresponding to the charged particle moving. Okay, if you are having a charged particle, clear, of charge E, this will be the canonical conjugate momentum. Okay, so what will be the energy of this kind of particle? So that's 1 by 2 m P minus E A whole square plus E phi. Okay, why this phi is a scalar potential. Huh? So this is scalar potential. So what you have identified, you can now identify this E to be the charge of the electron. Let's say, or the charge of the particle. Samajh? So global U1 does not give you the idea of the charge, clear? But the local U1 gives you the idea of the charge, clear? Samajh? And that charged field, okay, okay, the field with which it couples, so that's the massless field. Okay, one more point. If you see, since this is a coupling term, clear? Look here, this is a coupling between, let's say, J corresponds to the current of the matter field, okay? And this A is some gauge field, clear? Because this phi will represent the matter field, okay? So this is a coupling between this gauge field and the matter field, okay? And what is the coupling constant? E. So the charge turns out to be the coupling constant. Or more generally, you can introduce here fine structure constant. Okay? Got it? So we call a Lagrangian that describes a phi field coupled with scalar phi field coupled with the EM field. We call it as a scalar electrodynamics or the scalar quantum electrodynamics. Clear? Okay. So now let's look at what is the conservation here. Conservation rule in this case. So from this Lagrangian, okay, so let's write the Euler-Lagrange equations. So let me simply write. So it is not simply the J mu, it's actually the gauge covariant J mu. Okay, so let's consider the equation of motion for A field. So you are having partial mu, partial L divided by partial mu A nu minus partial L by partial A nu is equal to 0. So use this Euler-Lagrange equation. You will get this equation, partial F mu nu is equal to minus IE phi dagger partial mu phi minus phi partial mu phi dagger, okay, plus twice E square A mu phi dagger phi. Clear? So that is simply equal to minus IE phi dagger d mu. Sorry, yes. Phi minus phi d mu phi. Okay, so and we call this as minus E, this gauge covariant. So let's write this as J mu. Okay, so where J mu is this very object. Okay, so now let's make the derivative. So if you are having partial mu, like this thing, F mu nu is an antisymmetric quantity, so minus U. Clear? So now this is a symmetric object, this is an antisymmetric, this is equal to 0. Clear? So which implies you are having conservation rule for the J. Okay? So So that means instead of having the conservation of that J mu, okay, simple current, so you are having the current defined through the gauge covariant derivative. This very object is, okay, if there is no coupling, when you put E equal to 0, so then you are having this is the J. Clear? That will simply is the, okay, got it? So now you have got the idea of how, where the charge comes from, okay? Okay, and the point is whether charge is quantized, this also will not tell you. The analysis what we have done, so even in the standard model, we put charge quantization by hand. Okay, we don't have an answer for the charge quantization within this standard model. Okay, clear? So, and we don't have an answer within this formalism why charge has to be quantized. Okay, so clear? So we have just identified there exists a charge corresponding to a field of phi. Okay, for this scalar field of phi. Okay, समझ शवन? And if you take phi dagger to be equal to phi, that means a which field? Real field. Then the charge for on that field is what? 0. Clear?